instruction. So come back to our lab. Our lab here. Yeah. You have to add. The outcome is ability to perform a Laplace and inverse Laplace transformation. So ability to describe the concept of what is zero and poles in the LTI object system. Ability to determine a transfer function. Transfer function represents a system and plot the location of zero and poles in the S domain. Okay, we use the MATLAB. So this is a general definition of the Laplace transform. How you get the S domain here in the function? So you have to use your time dependent function times with the exponential negative st, the integral all of the item, then you can get the transform output. Okay, so you can read through this one later. Okay, this one is actually same with this. This one, that's how I explained. If left hand side is eventually you go to a stable state. If right hand side will eventually go to a very non-stable state. In middle height is a marginally stable. Okay. Compared to this one also, middle side is marginally stable. This is a Fourier. This state is the sigma equal to 0. Actually, this is called a Fourier transform. Frequency transform is a special case of Laplace transform. So if Laplace transform, maybe the sigma is less than 0. If sigma less than 0, this one eventually you go to the stable state. If sigma larger than 0, this one will go to the non-stable state. The system, I mean. Okay. So like the Fourier transformation, the Laplace transformation solve the differential integral equation. This is the table I just copy paste into my presentation slide. Actually, you can look through. You can reference here, refer here. Okay, now in this lab we have to use some new syntax here. Residual, AB, what is TF, transfer function, SYMS, what is this, symbolic variable function, Laplace. This is important. We no need use hand to calculate the Laplace transform. You can see the video here. This video, this link I will put into the link description in the description of the video. Later you can directly click and watch. This one, the Laplace T here. Actually, they do the Laplace transformation. This one here later you can watch these videos. You see what is the meaning of Laplace T. If I type this one into a MATLAB, then I can no need go through the very complex calculations. I just simply type these things in, then I can get the answer directly. This is inverse Laplace inverse Laplace command. Okay. So then this is partial fraction exponential. Later I will show you what is this. We do the example 4.1. We just copy and paste this into a MATLAB. So this example 1, then you can just press run. Exactly the same here. Is it exactly the same? So we run this. Running. We see the result down here. If you not understand what is system S and what is SYMS, then you can right click help. A little bit lag. Wait, whole computer. Okay, it's okay. Let me see here. The first one, what we know is y equal to exponent negative t. Here. Okay, y the answer is get into the register. So the fs is Laplace transform. Now let's say I have a function of y, I have a function y is a function of time, so exponent negative time. So I Laplace transform the exponent negative time. I will get what? I will get this one, 1 over s plus 1. Okay, so this pretty fs means I take the answer here, I make it, I rearrange it in the nice form, mathematical representation form, such as 1 over s plus 1. This one is a nice form. Okay, what you don't understand pretty is never mind, later you can search. But this is the Laplace transform signal. Fs is a Laplace transform signal, means s in the s domain. You see here, inside here doesn't have a t already, it's convert to s. This one original have t here, exponent can convert to x through the Laplace transform. Okay, you see what is mean by s, y, and s. Create a symbolic variable and function. What is the example? You can go look through. I see. Mean this one will get you let the t, define the t first. I mean, if not putting the t here means the y, we don't know what is inside here. If you put the t here means the exponent, they know, oh, this is a variable, this is a symbolic variable, means it's a package, it can be anything. You must define the t here. This is a definition. We define what is that. Okay, if don't understand this, what is this? Pretty, right click, help on pretty. Pretty x symbol, pretty print symbolic expression, means they display in a nice way. Okay, you can see the example here. Let's say I have to do some operation here. I get the answer is like this. B is like this. It's a array, one column, 2 rows array. So this is 3 over 2 minus 5 power of 1 over 2, means this is a square root divided by 2. Then this one 5 square root divided by 2 plus 3 over 2. You see, if let's say I write in a pretty way, so I can make a nice bracket here, parenthesis here. So inside that 3 over 2 minus square root of 5 divided by 2. This is nicer form. So you see here, this is also nicer form. Square root of 5 divided by 2 plus 3 over 2, also nicer form. But they make it in the 1 column 2 rows. It let you easily interpret. Okay, it's nothing much actually. The important thing is from y time domain, you see, time domain to s domain. You see, from time domain to s domain, this is what we want to learn using this command, Laplace bracket the y domain. This one also can change to entire thing is y, same also the meaning. Okay, the second example, let's say you have the question like this. This is time domain question. ht equal to 10 plus 2t plus 5 sine 4t. Okay, so how can we get into it? So I just copy and paste example 2. So make sure I have to define what is t, what is ft. Let the system know what is t and ft. Actually ft no need, also can. You can delete, but I let the system know what is ft first, also can. So ft equal to this one, all the things. Actually here a little bit wrong. This is if let's say this is ht, then here have to change to ht, because this one is this one actually what is it. If I use ft here, this one have to change to ft. Okay, now I use this is ft. Ft equal to this, so I Laplace the ft, means I Laplace transformation fst become the fs. So I can run here, same things also. I just Laplace the item. This is complex, a little bit complex, right? So if I want to solve with another long time domain signal combined with this, so it become very complicated. If let's say I Laplace it, I can get some simple result like this only. You see, 5s plus 1 2 times 2 divided by s squared. This is s squared, s power 2 plus 20 divided by s squared plus 16. This is the Laplace transform result. Easy only. Later we can use this to solve with another problem. Let's see. Then this one, okay. Now the example 4.2. Obtain the inverse Laplace transform from the given I. The first question is yt equal to 1 over s. 1 over s, how you get back the Laplace, the time domain? This is actually it's not a time domain, it's a s domain. This is ys. Okay. So this is a s domain. So later here, I can try here, then number 3 here. So same, I have to define what is s. Then this s they recognize because I define here. The Laplace, inverse Laplace of 1 over s become what? The result become 1. Why become 1? You refer to the table. 1 over s. Where is 1? The table is here. See? 1 over s. If you Laplace, inverse Laplace this one, then you get back this. You see, inverse Laplace this one, you get back 1. This is the answer. Okay, you see, you look back here, this one. Each of these you can refer to the table here. Let's say sine at, this one will occur in the answer. You see the answer here. You can look back, you can correlate back to the answer. But of course, if you look back at the answer, you have to do a lot of mathematical simplification here. But if you use a software here, then directly can get your answer. You see, s squared plus 16. What is 16? X squared plus 16 looks similar here, right? Because of x squared plus a squared. A is actually 4. A is actually 4 here. You see, 4 squared is 16. So this is y is 20 because it times it in front here. So later you can reverse engineering from here to time domain. Later we will show you. Okay. Okay, you see here. Let's say I have this one, hs equal to this one s domain. This one is s domain actually. So s divided by 4 plus 2s divided by s squared plus 14 minus 4 divided by x squared. This, what is this? Never mind, you just put inside, copy exactly the same. This is example 5. This one, s squared, and number 4, sorry, this is this. Then you just run. Okay, they know that fs is, this thing is go into the fs register. So inside fs here has this thing. Then ft, how we get the ft? This is s domain, remember? How I get the ft from fs? So I have to inverse Laplace. I take the fs, the input, all the components I put inside, inverse Laplace, then I get the time domain. You see, 4 over s is what actually? Actually, it's 2 cos. No, not 4 over s. Entire thing become 2 cos square root of 14t minus 4t plus 4. Because why 4 over s equal to, why is 4 over s here? 4 over s, if we inverse Laplace 1 over s, inverse Laplace 1 over s here become 1. That's why the output here is 4 only, because 4 times 1. See? This one. You can look back, what is that? Actually, 4 divided by 4t, what is 4t? 4t is from here. T is here, right? If you inverse, how you get t? If you what you have to inverse Laplace? This one, you see, 1 over s squared. Let's say this is n is equal to 1. 1 divided by s squared. If you inverse Laplace 1 over divided by s squared, then you can get t. See? This one. 4t. Why 4t here? Because of this one. 4 divided by 1 over x squared. 4 times 1 divided by x squared, actually if you inverse Laplace it becomes 4t. This is this. Okay, this entire thing here is this one, the item here. Why it become like this? Because x squared plus 14, you can see back, you can look back here, cosine here, x squared, I see, x squared plus a squared, but up here got s, this one up here got s, this one is cos, actually the cos function, 2 cos function. What is inside here? A. This is a, square root of a. Okay, this is the answer actually. Easy. If I put this pretty, then I can get this kind of result without the multiplication, the symbol multiply here. That really show the nice form. Okay.